Anti-aliasing. I ended my previous lecture with this slide. It shows multiple lines. Since these lines have been drawn as shown in the line on the left, it creates a flicker. This flicker is due to the sampling. Now, to give you an idea of what an effect a sampling can take place, let me see this helicopter as it flies. What is wrong with this helicopter? What we see is that the helicopter requires the propeller, the main propeller, to rotate to remain afloat or to fly. But in this case, what we see is that the helicopter is flying while the main propeller of the helicopter is static. This is because the videography of the helicopter, the images have been taken with a frequency which matches the rotation of the blades of the helicopter. Now there are 5 blades of the helicopter, so the period of capturing the images in the video can be 1/5 of the period of the rotation. Since we will not be able to identify between the 5 rotary blades, they look identical, so one rotary blade replacing the other exactly in this place will not show a change. It will look as if the helicopter is static. So it is important here, it creates a fallacy or a view which doesn't look real. Now, here I have a sine wave shown in a blue line with a pretty high frequency, but my sampling rate is much slower. And since if I sample it at a lesser space, what I see is the sampled points shown as green dots. They seem to indicate a different sinusoidal curve or a curve with a lower frequency. So there is an error which occurs due to this sampling process. This is basically due to the Naquith's limit. For a particular frequency to be detected, one requires the samples to be taken at a higher frequency. Errors. So similar effect is happening with our screen, where I am sampling the information into pixels, and therefore I lose the higher frequency elements of the line curve. Now, to give you some more effect of this quantization or sampling effect, let me show you some temporal aliasing there, which is sometimes known as the Moir effect. As I pass this darker ring behind this concentric gray rings, there is a flickering that occurs. This is because as this darker ring moves through the concentric gray rings, there is an effect of sampling which takes place because we do not see the rings when it is behind the gray rings, and therefore this sampling produces an effect of flickering. Similar effect we see here when we pass behind a chessboard. Let us see it again. Here you see this effect. This is called the Moir effect. Due to this flickering occurs is because of this sampling. The lower frequencies are lost and you get these effects. So same sort of an effect occurs when in our graphics when we draw lines or our image or draw polygons. We see here an originally a curve which is smooth, but when it is represented through a sampled pixel becomes box like as shown here, the original being rendered into this. Similarly, here the original has triangles, but triangles are represented as square pixels. The resolution is lost and the effect of the feature goes away. Similarly, what we see is that there is an aliasing here where you see that the effect of these squares are not seen proper for smaller and smaller squares. But if we have a mechanism of removing this aliasing, that is doing anti-aliasing, we can obtain figures as shown here where it has been anti-aliased. So here I have got a photograph where it has been pixelized. Because of the pixels, you see the aliased effect in the photography, and this is the effect of aliasing which has been removed from the photography. Upon this, so here I have a line and my sampling interval is shown in the square boxes. The square boxes are my pixels. And if I have a line here, the line will look something like this. The line below shows it smaller. So here it does not matter much. It looks like a straight line. But when we enlarge it, it certainly doesn't look like a straight line. What you see is something like a staircase. Now
A
this
normal line would look like this, that it will have these boxes. So this is how a line is going to look like. Now, as you see this, that if I see the thickness of the line at this location and see the thickness of the line in this location, what I see is that the thickness keeps varying. And because of this varying of this thickness, you will have an effect of flashing that was seen shown on those multiple lines. You get a flashing effect. Right. So now what we want is that we want to remove this. So one way of doing it is that instead of taking one pixel, if if this is my line, I take a broad line where say the line is of 5 plus pixels and 5 negative pixels, so the total length being 10 pixels. Right, so the line, what I have done is that I have made the line thicker. Okay, and in this process, what do I have? I have the small grids or the variation which is here, which is of 1 pixel, while the line thickness is of 10 pixels. So the variation has reduced to 10%. Here the variation was of 100%, here the variation is of 10%. Right. But then this makes a broad line. So any line that I want to show will have to be thicker in size. So I will not be able to plot thinner line. So the idea behind is that if I want to smoothen this, I will have to take in technical words, I will have to take a Fourier transform of a line of a square square wave, which is basically the line thickness. If I plot the line thickness, if I call this h and I will call this an intensity, this is the line thickness equation. And this, if I take this function, the in the frequency domain, it becomes a sinc function. Sinc function is something of this kind, where I have got the function with is equal to sine of h upon h. Right. So this is a sinc function, but a sinc function is not so good, because see, what you see is that here it is becoming negative. At these locations it becomes negative. So talking about negative intensities become difficult. See, what you have is positive counts, negative counts cannot be there. What you can do is that you can make it 0, or you can take the absolute value of it, so then you will have the harmful change direction, but still it will be wriggly. So it's much easier or better to choose a function which is closest to this is a Bell function or a normal distribution or a Gaussian function. Okay, a normal distribution or a Gaussian function can be represented by a curve which looks something similar to this. Let me just draw it properly. It's a symmetrical function, though my drawing is not symmetric. So the function would be the intensity. This is my h, h being this axis, h, this is the direction perpendicular to the line, it is not the direction of the pixels. So my intensity would be I of h is equal to some I naught e to the power minus h square upon 2 sigma square. So this is a Gaussian distribution of a line. Now, a Gaussian distribution of a line. So
If we
now,
take a profile around the line, that is, if we convolve the lines with a function, say a Gaussian function, then the lines would be spread over a larger number of pixels, and therefore the effect of this box-like effect will go away. But however, if I spread the line over a larger number of pixels, the sharpness of the line goes away. And therefore, to maintain the sharpness of the line, instead of using a flat curve, I could use a varying curve, a curve which will damp exponentially down, making the line look as sharp as before. So as we see here, the same line on the left can be shown with shades of different colors. We can, of course, shade the pixels with different intensity values. We have an 8-bit number intensity value, so we can have 255 shades, and we could vary between 1 to a 5-bit number grayscale, which could define the shades of this line. Now, if we define the shades, the line would look something like this. What you see here is the darkness of the line depends on the distance of the center of pixel from the line center. The further the pixel is from the line center, the less darker it is. So how do I find what should be the intensity of these pixels from this distance? If I know the distance from the line, how do I get this intensity pattern of the pixel? Let us take a line and we would like to have a gradient profile of the line. If we take a cross section of the line and find the intensity, we could fit an intensity of this pattern, which could be a Gaussian cross section. A Gaussian cross section is given by I of h is equal to I naught e to the power h square upon 2 sigma square, sigma being the spread or the cross section of the curve, where the curve reduces on either side with increasing h value. We could represent this curve with using more pixels. So we could have the curve with more pixels, or we could also represent it with lesser pixels depending on our choice. We could also choose different sigma values to have a sharper line or a flatter line. Now let us take an arbitrary line which has a slope m, and we would like to find the cross section of this line. As shown again, we would fit a Gaussian cross section. Now this Gaussian cross section will depend on the direction that is perpendicular to the line h. So if I need to fill the intensity, I have to fill up a line which is perpendicular to this line, which is much more costlier and time consuming. That is, we need to again run an algorithm, a line algorithm, to find the pixel points and then fit these pixel points with the intensity value. Now, instead of that, can we choose a vertical set of pixels where we could go to a particular pixel value of the line, then move up by some delta y pixels, and we could start coloring them and move up to pixels of delta y below the line center. So what you could have is a set of pixels as it is being colored here. What you see is that you can have these blue pixels in our code to do it. So to do this, let us take this set of remove these pixels from our image and see how we could mathematically derive the distances which is available here. So if I have this point P of x, the distance is h, and the other distance is delta y. Now what I have is, if my angle of the slope is theta, then this is also my theta value, and therefore I can say h is equal to delta y cos theta. So I can determine h in function of theta and delta y. So knowing delta y, I can easily find out what h is knowing theta. Now theta is dependent on the slope. As we see, the slope m is tan theta, and from where I can derive cos theta as equal to 1 upon under root of m square plus 1. And if I replace h square by the function h, which is delta y divided by under root m square plus 1, I have the equation given below. Now surprisingly, if you will notice that the equation, that is I in function of delta y, is also, or is, a Gaussian function by itself. Only that this particular Gaussian function has a different cross section. So if I choose this cross section to be sigma y, then this cross section can be determined in function of the slope of the line, that is the cross section of the line that I would like to have, that is sigma, multiplied by under root of m square plus 1. Now please note, if I take m is equal to 0, I see that the sigma of the line, sigma y, becomes equal to sigma. So now instead of drawing the line along the perpendicular axis, I could choose a point at the base here, move up by some delta y pixels, and start coloring these pixels with the function given here, and this would have a similar effect as if having a cross-sectional cut or cross-sectional filling in the axis perpendicular to the line. This will help us in our code. So if we use Bressenham or DDA, we could just move by say 5 pixel up, start coloring, move to a 5-6 pixels below, and do the coloring process. Now this is what you will have. So similarly, instead of using a Gaussian cross section, I could use a conical cross section as shown here in this equation. But for a conical cross section, I will have to make sure that the intensity doesn't become negative, and to assure this, we will have to fix or put a limit to delta y as below delta y max, which is equal to under root of m square plus 1 divided by alpha. Alpha is basically the slope of the conic section that we would like to plot. Now please note the previous function, the Gaussian cross section, is a function which will never become negative. It will become 0 only at delta y or h tending towards infinity. Similarly, here is a conical section, and this conical section could be seen as a cross-sectional plot that we could do of this kind. And similarly, instead of doing it in the axis perpendicular to the line, we could take a vertical axis and keep coloring it as shown in the function above. We could also have a simple function which is a box curve, where I could have that if h is less than b, it is equal to an intensity I naught, and for h greater than b, it becomes equal to 0. This filter makes the line thicker, and therefore it still will remain like a boxy, but the effect of the box-like effect will be reduced if I take a width 2b as equal to 20 pixels, then my variation would be of about 10% of the line width because of the boxiness of the pixels. So I have reduced from 100% to a 10% accurate line, and this would look like a more continuous line. Only problem with this would be that the line will become fatter and broader, and therefore sharper lines will not be easily drawn through this filter. We would then use either a conical filter or a Gaussian filter to anti-alias a sharper line. Now, conical filter, simple set of pixels to a multiple of the distance. Gaussian filter store pre-computed values in a lookup table, and each time you move 5 pixels above, you start coloring those from an intensity array. Move from our intensity array could be of 10. So I could move from an intensity of ij uh, 0 to ij10, where ij5 being the center of the line. So I could just keep coloring them by storing this from the lookup table or an array. The thick line stores the area or the extension of the lookup table, and the value would be the same. The limits need to be just noted, and you can keep coloring them in the same manner on the column wise in the line. Anti-aliasing a line, obvious need a gray level display in order to remove the aliasing. That is, if I have a simple binary display, it will not work. I need a shade of intensity, and therefore I need a gray level display system. So it could be an 8-bit display system. Convolve lines with filter functions for the pixels. So we could use box filter, which is an area sample, convolution with conical filters. But the price to be paid is the trade-off of the spatial resolution. The line will appear more blur. Its exact position is no longer as well defined. In practice, the contrast of the line is much reduced. So a line which looks very sharp won't look as sharp as it is when we do this convolution. Of course, here what we have seen is that we have fitted a curve, assuming that we do not have many lines in the image, or we could take the image and do a convolution with a Gaussian function, and that would give us the similar effect of, fitting a profile on the line. But if the number of lines are lesser, convolution would be much costlier. It would be much easier to fit profiles on each line. Anti-aliasing by area sampling. So up to now what we have seen is that we have fitted a profile curve. Now can we assume a sampling of area? Now if we assume the line to be of some thickness 2b, sorry, if we assume the line to be of thickness 2d, then we could assume and see that there are some pixels which are half occupied or quarter occupied by the line. Now, of course, I cannot fill half the pixel or a quarter of a pixel. What I can do is that I can fit a quarter of a pixel, or I could fit the whole pixel with that intensity which is quarter of the total intensity of the the pixels which fall totally in the line. So this level of intensity will depend on the area of the line, which is area of the pixel which is part of the line. Now the problems are: equal area contribute equal intensity regardless of distance from the line center. Small areas in the pixel center contribute as much as a small area at the pixel edges. So this is an effect. Now this, if the whole pixel is part of the line, it will have the same intensity as the pixel which is absolutely in the center of the line.
Is that you have an intensity pattern which is I of I comma j will be equal to weight of ij times I naught. Now, supposing I have this line, wait a second. Okay, if I have this line, now please see, just I'm just exaggerating, say that this pixel, okay, is now what you see is that this is a full pixel, right? And what I see here is a portion of the pixel is actually colored. In reality, I cannot color half a pixel. It has to be a full pixel. But what I have here is, if I draw this pixel in big, little bigger. Okay, if I draw this pixel a little bigger and supposing this is my edge of the line moving on this pixel, right? And so, okay, so this is my area. I will call this area A of I comma j, right? So I will need this weight I comma j is equal to A of I comma j upon A naught. A naught being the total area of the pixel. So this is the weightage factor in which I need to fill the pixel. Now what I know is that this thickness, supposing, is b. I know that the slope is m of the line, right? If I know the slope is m of the line, supposing I tell you what is the, say, PA and PB, can you determine omega ij? So this is the.
So if I take a pixel area as A naught as a unit square and assume it to have a weight of 1, so we could weigh the line. Supposing the line is the portion of the pixel which has been shown in red and has an area A of j, that is area, it has an area of A of ij, then the weight factor can be defined as omega ij is equal to aij upon a naught. If aij is in units of pixel square, then obviously it would be normalized since a naught is equal to 1 pixel square. Pixel color is determined by computing the amount of the pixel covered by the line, then shading accordingly. Easy to compute given a reasonable results. So here I have the intensity which I can compute as omega ij, the weight factor, which depends on the total area covered, times the total intensity I naught. Now, if the total pixel is part of the line, omega ij will be equal to 1 and Ij would be equal to I naught. Now here I have a line which is defined here in red, and I have taken a particular pixel Ij, and this is my thick line which you see, and I see these pixels which are half covered and some pixels are small partially covered. How will I be able to color these pixels is to be seen. 2D being the thickness of this line which I would like to shade it with. Now if I take a broader line, this is to make the diagram much more clearer. I have this pixel P of xy, and I have this distance d, which is the distance from the center of the line, perpendicular distance to the center of the line. And I need to calculate again delta yd. What we have seen, delta yd can again be written as d times under root of m square plus 1. Yt is equal to y plus delta yd, which is given as y plus d times under root of m square plus 1. I have further enlarged it and I have marked the pixels. The squares that you see is of each square represents 1 pixel. Now supposing I take a point y of t I, which is shown here, and the point which is closest to the edge of the pixel can be defined as j, which is equal to int of y of t of I. Now if I take this triangle which is there on top, this triangle is defined and is the same for every section of the line. This depends on the slope of the line. As we have seen that if a pixel is advanced for lines for m less than 1, while studying DD algorithm, we have seen that if you advance by 1 pixel, the y-axis advances by the level of the slope, that is m. So the height of this triangle would be m, and the base of this triangle is the width of the pixel, which is 1 pixel. Now if I have m in pixels, then I could determine the area of the triangle AT as equal to 1 upon or half of m times 1, which is m by 2. We could then also try to determine the area below the triangle, which is a rectangle, and the base of the rectangle is again 1 pixel. The only thing that varies is delta I, which is the height of the rectangle. That is y of t minus integer of y of t of I. And of course, if I have this as the height, and I could find the area of under this rectangle, this area of the rectangle can be defined as A delta I is equal to delta I pixel square, which is equal to y of it minus integer of y of it. The units would be in pixel square. So if I'm enlarging my region, and if I enlarge this region, and I have seen that this is my area of the triangle, and this being the area of the rectangle, the total area is determined by A of ij, which is equal to at plus A delta of I, which is equal to m by 2 plus delta I, and delta I can be replaced, and we have the final equation, which is m by 2 plus y of t of I minus int of y of t of I, which is again in pixel square. So if the total area of the pixel being a naught, which is basically 1 pixel square, then the weight factor, which is defined as the area aij upon a naught, is basically the area aij, since it is in pixels, as given in the equation below. But what happens when this m plus delta I becomes greater than 1? So let us see this situation here. Here I have a situation where I have got the line which has become greater than 1 pixels, and where m plus delta I is greater than 1. Please note the slope is still less than 1, but I could have such situation where I could have a line cutting in the middle of the pixel, and I could have such an effect. So in this case, I will have to make a special consideration. So this is the case where it is m plus delta is greater than 1 pixel. So let me calculate the area which has overshot outside the pixel, and this area can be calculated by calculating this h. H is nothing else but m plus delta I minus integer of m plus delta I. So basically here I will not have this m plus delta will not be greater than 2, because I know that m is less than 1, and for m less than 1 I will not have such a case. Maximum my area of the rectangle could be the area of the pixel. H will always be less than 2. So here H is defined as m plus delta I minus int of m plus delta I. We could then calculate the base, and this base is defined by the relation of the slope. M is equal to h by b, from where we can easily find out b is equal to h by m, and therefore we could then find out the area of the triangle which is overshot out of the pixel, which is a tau, which is equal to half of hb, which is equal to h square upon 2m, which is given by this equation shown below. Now we could put this condition: if m plus delta is greater than 1, then a of ij, which has been calculated previously, is equal to A of ij minus A tau, and consequently omega ij will be equal to A comma j, A of ij upon A naught. And we could also find the area of the upper pixel, that is A of I comma j plus 1 is equal to A of tau, which is the top triangle which we have subtracted from the previous area. And this weight also could be determined, and we could also in this process increase the count, the j count, by 1. Now for slope greater than 1, like DDA, we could flip x with y and y with x, and therefore my intensity can be found out. A of ij is equal to omega ij times I naught. This is one technique which is analytically proven, but what could also be done is by doing a super sampling. You break a pixel into a grid of smaller grid sizes and try to see how many grid values of the pixel is within the line and how many grid values of the pixel is outside the line, and in the process the grid centers, that is, grid centers are inside the line and grid centers are outside the line, and in the process you could calculate the area within the line or the area outside the line. To speeden up the process, instead of using grid, I could use a random number generator where I can use a method like the Monte Carlo simulation to get the values of the intensities within the line, which the number of hits within the line and the number of hits outside the line on the total pixel, and that would determine the area. Similarly, we could use a Poissonian distribution of random numbers and do the same thing. We could also jitter every point a little and do the same thing. This is basically the methods of supersampling within a pixel, and through simulations like of Monte Carlo, that you determine the area within the line and the area outside the line. Now, there are situations where I could have a polygon where I have a foreground and a background, and I need to make a decision of what should be the pixel and how much should I illuminate the pixel. For instance, I have a polygon which is shown here as red, which has an area of Aij, and the complementary area which is occupied by the background, which is shown in blue, which is A prime ij. Now, how do I determine in the edge what should be the value of the pixel, the intensity value of the pixel? So I have the weightage of the red area of the polygon or the line is given as omega ij is equal to aij upon a naught, while omega prime ij can be determined by a prime ij upon a naught, which is equal to 1 minus omega ij. And therefore the intensity color could be a mix of the two colors, as shown here, where I have the the red color I see is weighted by a quantity omega ij, while the background color blue IB is weighted by 1 minus omega ij. So in this respect, I could color two, two polygons or have an anti-aliasing effect. To anti-alias a line, we treat it as rectangle, and anti-aliasing a polygon is similar. Some concerns micropolygons smaller than a pixels, super sampling. There may still be polygons that slip between the cracks. We will see this when we will study the fill algorithms.